Alright, now that we have seen how multiplexer works, and we know that multiplexer is a selector, a device that selects inputs. And if we have multiple inputs, then multiplexer will select at one time which input can goes to the output. Okay, now we're going to look at some multiplexer application. Okay, multiplexer uh, can be found in many application, such as for data selection, routing, parallel to serial conversion, operating sequencing, waveform or logic function generation, and so on. Alright, now let's look at how multiplexer can be used as a logic function generator. Okay, multiplexer can be used to generate combinational logic function in sum of product form. Remember sum of product that we have seen in chapter 4. Okay, and we have also learned how to design the logic circuit for sum of product from Boolean expression. Okay, now we can use multiplexer to implement that Boolean expression. Okay, and why do we use multiplexer? Because it can greatly reduce the number of ICs and can make design changes much easier. And the variables are connected to the data select inputs, and each data input is set to the logic level required in the truth table for that function. Okay, so let's look at an example. Okay, so let's say we have this SOP Boolean expression here, Boolean function here. We have f and three variables x, y, z, and this one, if you remember, this is an SOP expression. Okay, and f x, y, z is equal to SOP 1, 3, 5, and 6. So design this logic function using an 8 input multiplexer with 3 selectors, S2, S1, and S0. So be careful with how many selectors, what type of multiplexer we're going to use, and how many selectors we're going to use. Okay, so how do we solve this problem? What are the procedures? Okay, the first one, we need to list the truth table and identify how many selectors we have, and the first n minus 1 variables will be connected to the selectors. Okay, and then for the rest of the if there's still some variables that are not connected to the selectors, we can connect them to the input. Okay, and based on the truth table, we connect ground and VCC to the corresponding data inputs according to the truth table. So how do we do that? Let's see how we can implement that. Okay, now let's look at our Boolean expression here, our Boolean function here. F x, y, z is equal to SOP 1, 3, 5, and 6, which means that the function f has high output at 1, 0, 0, 1, 3, 0, 1, 1, 5, 1, 0, 1, and 6, 1, 1, 0. Okay, if we have our, let's say we have our truth table here, so the output only high at 0, 0, 1, so put that as 1, and 0, 1, 1 here, 1, 0, 1 here, and 1, 1, 0 here. So the rest are zeros. Okay. All right. Now, our multiplexer has 3 selectors, so no problem. All the input will be the selectors here. What about the data input? So which data input will be, the next step is to determine which data input will be connected to low, which is the ground, or connected to what we call high, which is VCC. Okay, so to determine that, it's very easy. Now look at all the ones, all the output ones So first we label the data input number. The data input number, this one is 0, 1, 2, 3, 4, 5, 6, and 7. What we're trying to do now is we have our multiplexer, let's say like this, and the selectors here, the X, Y, and Z. Now this multiplexer has 8 input. 3, 4, 5, 6, 7, 8. Okay, it has 1, 0 until 1, 7. Now what we're going to do, and it has only one output F. What we're trying to do is to determine which of these input line, I0 until I7, is connected to the VCC. Let's say we have a VCC here, and which inputs will be connected to the ground. Let's say we have ground here. Okay, so in order to do that, we need to look at our truth table. Let me just write this again properly. Okay, this one data input I0, I1, I2, I3, I4, I5, I6, and I7. Okay, now which input will be connected to which data input will be connected to the VCC? Now look at our output here. We only the only output the only combination of input that produce output high are 1, 3, 5, and 6. So therefore 1, 3, input 1, input 3, input 5, and input 6 are the only ones that will be connected to the data input, the source or VCC. Okay, so data input 1, 3, 5, and 6 will be connected to the source VCC. And what about the rest of the data input? Since the rest of the data inputs are the output of the multiplexer is 0, so therefore all the rest of the data input will be connected to the ground. Okay, so remember when whenever the output of the multiplexer is 1, those data line or input data input will be connected to VCC. So whenever there's 0, for example here, 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 and here, that data input will be connected to ground. Okay, so how do we implement that? All right, now that we have our truth table, so how do we sketch or design our multiplexer? We know that only data input 1, data input 3, 5, and 6 will be connected to the VCC. So we just simply connect that data input, the input line, to our VCC. 1, 3, 5, and finally, 6. Okay, and the rest will be connected to 0 or ground. Okay, in this case, we connect it to our ground line here. And lastly, 7. All right, so that's it. That's how we develop a multiplexer that represents this logic function. All right, so be careful with this kind of problem. So you need to identify first which data input will be connected to the VCC or high, which data input is should be connected to the ground. Okay, so please be careful with that. And this is a different view of the same solution. Okay, this one is from the textbook, and on the left here is from the textbook, and on the right here is I implement this one using multisim. Okay, you can try to do this one using multisim later. All right, try to design the multiplexer using multisim software.